Because two is better than one.
Oh, it's any kind of phone.
HBL. Yes, that's HBL. Yeah, but why two lines?
By definition.
The French will be quite
Yeah. You have the power. You have to hold it really close. Yeah, that's normal. That's normal. I'm getting this. Oh, you got audio on the mix. I think I know.
It's all about
The phone.
I've got the power.
Alright. Hello and welcome everyone to this talk about overscan and sync scrolling. I was asked half a year ago to come and do a talk on the latest discoveries. And I heard more rumors about what I'm going to talk about since then than I think I put into slides. What we're seeing is, of course, one of the effects from the demo that Sync showed at the demo competition yesterday. The one-way SDFM, full screen, existing, true color scroll test. A special version that runs in Atari. The release code does not, Atari does not emulate the sync tricks that I do. And I'm going to try to exit Atari, because what you all wanted to see when you came here was a PowerPoint presentation.
Nice white screen.
So let's try to get that PowerPoint presentation.
Ooh, nice place.
And my computer is trying its best to show that presentation. I think I screwed all that up by wanting to get Atari there as well. Alright. Enjoy this screen until I get this back. Yeah, I like unfortunately, the PowerPoint presentation did not run on the computer, so we had to use my computer instead. Alright, you got it. I'm going to talk about a few things here today. I'm going to talk about overscan. I'm going to talk about sync lock. And I'm going to talk about sync scrolling. And all these things, of course, tie a bit together. I'm going to start by doing a bit of a history lesson most of it goes to LGBTK, Holosmos, who has done an immense research into sync switches on the Atari scene. Very, very grateful for all the work that he's done that I've had to build upon. Ejor on the Atari forum has done some pretty cool research that I'm going to reference as well. Alien is the connection. Of course, everyone knows that he's done pretty much the seminal work in the beginning on sync scrolling, the glue and the shifter. And there is some of me in here as well. That is not known until this presentation. So let's start with those again. I am definitely sure that everyone here knows what OpenSync is. Alyssa invented it. If there's anyone who knows whether Alyssa was influenced by how we did things on the Commodore 64, that would be really good to know. He was. Excellent, thank you. That will go into the history books. And first, of course, released by the exceptions, September 8th. That's, of course, that started out the whole thing. First time I saw the little border removed, I was amazed. I've been living with a green desktop and with borders around it. I thought that this was really awesome, that this was possible to do. That's, of course, done by going 60 Hz and then back to 15 little border. The same trick, although it was scan line, removes the right border, again done by the exceptions. Then it took a while until we got the left border removal by the TNT crew, depth of the left border, which is done by going to high resolution instead of 60 Hz. For a long time, I thought that my computer actually started outputting dangerous frequencies to my TVs whenever you went to high resolution, but so I thought it was best to do that in very short intervals. That left border wasn't stable. For many, many months, I thought that the depth of the left border was supposed to be only every 16 pixels. The rest were supposed to be black, because that's what it looks like in my computer. Upper border, using 60 Hz, first time by Hexaflex International in July in 88. So in the BBL, you go to 60 Hz, and then as soon as you kind of get the first channel, you go to 50 Hz, and that gives you an upper border that on monitors that can handle 60 Hz looks pretty funny. On TV sets that can't handle 60 Hz, everything gets wavy or offset by 4 pixels out into the left or other strange effects. A lot of people who released upper border demos did not know this. First full screen was done by Omega in the Omega demo in December 88. My computer, yet again, showed every other 16 pixels black, and I thought that was a pretty cool effect. Seems to be pretty common. As far as I've heard, that full screen basically only worked on the Flying X machine. Upper border in 50 Hz, first released by TCB in a demo the week after the Omega demo at the Swedish New Year demo in Milan. TCB removed the upper, the left, and the right, and that's pretty strange. Why not remove the lower border as well, since everyone knows how to do that? I assume it's because they got the code from level 16, and they were not allowed to release full screen before the Union demo. No one seems to be protesting. I've checked the code, it's exactly the same.
It's
The guys are on the tour, the level 16 guys, so you might want to check back on that particular one. But I think that memory says well that one can be done.
Alright, I'll check with them when they come back. If I was level 16, I would have been pretty mad at SB releasing a full screen a few weeks before the Union demo, since they used the same code. Anyway, it used an upper border in 50 Hz. It had lots of bugs, that 3-border screen, and I will get back to that. And the first full screen stable by level 16 in the Union demo. And what's amazing with that full screen code is that it's without modification used today. So at that point in time, the state of the art of full screen, of border removal, had already been researched and done. Now I've commented upon this being stable and other full screen lines being unstable. Now what do I mean by stable and unstable? Here's a diagram stolen from Alien about the different chips that are involved in doing these tricks on the SD. We have the glue, which is the glue in the machine. It deals with a sync timer. It reads the state of registers and it then outputs different signals. It tells the video should go into different hertz, refresh rates, counting cycles, etc. We've got the MMU, possible for reading the words from memory that the MMU has told you to read, look it up into the Palais and rotate the bits. Everything about the stable and unstable has to do with the shifter. Because when we do full screens, we only affect the glue. It's the glue chip that will manipulate. And the shifter tags along, and we hope that it will do the nice thing. And as we've seen with the every other 16 pixels black and unstable and stable, it doesn't really want to do that.
Are you sure it's a shifter problem, but the shifter only displays the data the MMU puts on its address bus?
I am definitely sure it's a shifter problem, and the rest of the presentation will go into more details. Alright, so what are the commonly used variants of stabilizers? How do we deal with the unstable shifter? The gold standard, which was already done in the Union demo, or the TCP3, is to, at the end of the line, switch to high resolution, which for instance will make the pixels black since they're now outputted on mono, the mono pin. Wait a lot for cycles, or 8 as well as is due to the move, and then switch back to low resolution. So that's fine. You get a black vertical bar at the very right of the screen. What happens is that the shifter is clicked. Now this stabilizer can hold many names. Closing the right border is one of them. What it does is to make sure that the shifter is in a known state before the next line begins. There is another variant though, as far as I know, invented by Mastic of the Matrix. Don't know why, but thanks for providing that variant.
I like colors instead of black.
Colors instead of black. I think that's a wonderful reason for doing it. Going to medium resolution, 4 cycles earlier, and staying there, and of course the shifter actually works differently in medium compared to high, so doing this 4 cycles earlier is the correct thing to do.
Oh, and didn't want to use registers, so I moved immediate to address. So yeah, that's the reason. Oh, it works. Oh, fine.
I love this. So the reason you're doing 4 cycles earlier, which is the correct thing to do, is because you didn't want to waste registers, which meant remove instructions from 12 cycle system of beats. It's a very good invention. It's used today, and it actually will influence. So the difference between these stabilizers will actually influence some other things that we'll get to at the end of the presentation. The first one, by accident, cancels H flag. Now that's a TV signal, which basically tells the TV or monitor, I'm not sending any data now, so that you can be really, really sure that when you see a pulse next, it's going to be the end of the line or the beginning of the new line if you want, pulse, the sync pulse. The first stabilizer cancels that, and any pixels that you have at the far right of the scan line will be displayed up until the sync pulse. It's fully possible that the screen will actually not work and not show you full screen if you have color data there. And the other version, of course, if you have pixels where the shifter goes into medium res, it will show that those pixels in medium resolution. So this was a switch done at the end of a full screen line. And if you've ever done full screens, you know all about switches. Forget all about switches. For the rest of this talk, I want you to forget all you know about switches. They're completely uninteresting to talk about when we do full screens. I have analyzed how the glue works in ST and STD and written down a state machine, because there is no chip in the Atari that sits in that if then does. A register is checked and an action is taken depending on that register. So this is what the glue state machine looks like on the ST. To the left you have cycles as seen by the CPU when the CPU does a move instruction. I'm only interested in being able to manipulate registers, so I count from moves. So you can see at cycle 4, if the resolution register is high, it will start displaying the screen. Another interesting point is at cycle 164, if resolution is high, it will stop showing the screen, etc., etc. There might be some interesting things still left to analyze, but this one it's actually pretty complete. So, you might have heard about wavestates. were first talked about in 2006 in a thread on Atari forum where Paolo Simos and Idro were discussing. And they were talking about how code sometimes was different when the machine was cold and when it was warm, when it was booted up. And it was persistent, so it was when the machine was powered on, it would stay the same if you reset. And this, they then documented, changed things in how you could do manipulation of different registers. In 2012, Paolo made a comeback after being absent, and now decided that there were not just two wake states, there were four. The two earlier ones have been subdivided into two more. And to be able to see these, your code needed to be precision at 2 cycle intervals. Never demo coder, basically up until then, knows that on the Atari everything is 4 cycle long, which isn't true. Oh yeah, actually I want to mention that. Even Sync's code in 89, 90 worked under the assumption that Atari had done multiple revisions of the hardware. We talked about, oh, your machine is different from mine. If I want to open the lower order, I need to do it 40 cycles earlier, etc., etc., etc. There are differences in the Atari machines. The biggest one for these effects is that the machine can be 8.007 MHz CPU, 8.01 MHz CPU, 8.02 MHz CPU, that's the common one, or 8.05 MHz CPU for NTSC. The CPU clock, if that is different between machines, the MFPs. So if your code relies on setting a timer and doing something when the timer when the timer throws, you will end up at different places. So that's why opening the lower order, for example, maybe the top order, works different than different hardware. But when it comes to opening full screen scanlines, there are no differences between Atari chipsets. They all work the same, besides ST and STE. And why is this? So on the ST, clock cycles get propagated between chips. So the shifter gets 32 MHz, and then the MMU gets 16 MHz, and the glue gets 8 MHz, and the CPU gets 8 MHz. But the glue and CPU aren't synchronized. So randomly, when you boot up your machine, they can be offset from one another by 0 to 3 cycles. So whenever the glue reads at a certain point in time, at which it believes to be the point in time, might be offset 0 to 3 cycles from the CPU's point of view. And those are the 4 wake states. So if I want to manipulate registers at cycle 56, in wake state 1, the glue basically understands my code from the CPU's point of view if I've done the modifications at cycle 56, both for frequency and resolution. What's called wake state 3, the resolution register is actually read, I need to manipulate it 2 cycles later, or I can. Wake state 4, both frequency and resolution registers are 58, and wake state 2, which actually seems to be the most uncommon one. I need to modify the registers at 58 and 60. Now these sound like small differences, especially since our code usually runs at 4 cycle intervals. But look at this. The resolution register, when it's read by glue, as seen from the CPU, between wake state 1, very common, and wake state 2, quite uncommon, actually differs by 4 cycles. So we would kind of expect there to be some demos at some point in time having been written that actually do not work as they should in one of these wake states. One of them is the famous D-Speedstone effect in the Swedish year demo. I actually remember, when I did this research, I remembered that I had seen that screen at different times when I booted my computer. The distinct PCB log in the middle was either centered or off to the left. So I thought that was part of the demo. Don't know why, don't know how to do the random thing, but sure, at some point in time it's a bit off to the left. I analyzed the demo now, disassembled it, and it actually is that in wake state 2, they will fail to open the left border, which is the common thing that happens, and thus the log will be centered a bit to the left.
Is it
possible to detect the state?
Yes, it's possible to detect states. Maybe I should publish that source code. I will publish that source code to detect the state. Publish most have written a program so that you can boot your computer and see which wait state it's in. But if you do a carefully selected scan line where you try to open different borders and stop borders, etc., and you count at the end of the scan lines how many bytes long was this scan line, you can actually know which wait state you're in by just doing that in one scan. Of course, having a log that's sometimes centered and sometimes off a bit to the left would be an interesting thing to ponder about for sync scrolling. I don't know if that influenced TCP's invention of sync scrolling. And there's a ULM full screen that does not work in WaveState 2. I forgot the name of it. Please help me out.
Oh, I don't know which one it is because I have problems to get into the state.
As I said, WaveState 2 is difficult to get to. Gansky hasn't his problems getting it to himself. But it's one of your full screens does not work in WaveState 2 either. And it's a combination of how we do two-cycle granularity and the WaveState. So how do we get to two-cycle granularity? How can we do that in the atomic? Old school. There's an instruction called exchange registers. It takes 6 cycles. So we would expect that to always take 8 cycles on the atomic. But instructions actually can be interleaved depending on when the user was. So if you do an X instruction followed by move, the move will actually be offset 2 cycles from what you would expect from a move. So you are able to do moves with 2 cycle granularity. And since you're able to do that, you can actually work with the glue in all the different wave states. And this sounds really complicated, but to the effects that we're soon going to talk about, you actually need to be able to do this. You need to be able to detect which wave state are you in, and then manipulate the glue depending on that. So I talked a lot about the SD and the need for stabilizers. So I just want to mention that there are stabilizers on the SDE, and you don't need stabilizers because there is a full screen that's 224 bytes instead of 230, where you don't need to clear the shifter. That was actually invented by them, Oxley, without knowing it. In a discussion on the Atari forum, Leonard all of a sudden wrote, "Oh, I have 178 byte and 180 byte understandings. Can anyone else see if they have them?" And people said, "No, we don't." And then that was forgotten. And then VHS, and I sort of forgot the person at VHS that reinvented this. Sorry? I don't think it was evil, no. But in any case, so when I looked into this, and I'll get back to that state machine, I realized this was exactly what Leonard has seen on his SDE, and everyone who said, "No, you're wrong," it's right on SD. And of course, it doesn't work on SD. So this is the glue state machine for SDE. There are 2 big changes. One, the first position, we're deciding where to start or when to start the line, has been changed from cycle 4 to cycle 0. Sorry. That's why you'll see a lot of demos written for the SD that fail to open the left border on SDE. They're one not off. That's why I had re-released 2 of 6 full screens 2 years ago to be SDE compatible. The other one is something called preload. So we're taking the decision much earlier when to start the normal scan line, 16 cycles earlier actually. There's a decision-making preload. Anyone knows what that is? Exactly, because of hardware scrolling. The SDE needs time scroll. So to be able to time scroll, it needs the data 16 cycles earlier than SD. And there's an algorithm running. The chipset, the GSD-MC of the SD is much more advanced than the chips of the SD. So there's a bit of an algorithm running that actually handles, oh, I'm preloading, which resolution is am I in, and when should I stop preloading? And you can manipulate that algorithm. So you can start the preloading, and it thinks, oh, I'm going to preload 4 words, I'm in low resolution, and you immediately go to high resolution. And it says, oh, I'm not preloading, I already got my word, and it collects it. And this is how the SDE short left border, which creates a stable SDE full-screen scan line, how that is done. There are also 2 other scan line lengths you can get that they're is still the state of the art. I watched demos here yesterday that we're still using that full screen scanner. With the knowledge we have today about wake states and the state machine, can we do better? And this is a good time for me to drink some water. And we're back. There's obviously something we need to do at the start of the scanning. It's not a full screen scan line if we actually do not start the line. That check on SD is cycle 4. We need to go to high resolution to start the scan line. Let's just do that, nothing else. Let's just go to high resolution. However, we can't stay in high resolution forever. At cycle 30, we actually really need to be in low resolution. Otherwise, the computer will start lagging and asyncing. It will screw up bad in the rest of the scan line. Let's go to low resolution before cycle 30. We need to be 50 hertz at cycle 54. Else it will be an NTSC scan line of 5 cycles. Let's make sure we're at 50 hertz at cycle 54. And let's stay 50 hertz until then. But, well, we want a full screen scan line, so we actually need to go to 60 hertz when the check is made for whether the scan line should end in pod. This is all we have to do. An optimized full screen scan line, only talking about the glue, does 4 things. It goes to high resolution at cycle 0. It goes to 50 hertz, a suitable place at cycle 8. It goes to low resolution at cycle 16. And it goes to 60 hertz at line 378. These are not switches. The glue does not care about switches. It only cares what the register is at a certain point in time when it reads the states. This full screen scan line, these 4 instructions, actually does work sometimes. But I would not suggest you use it in a demo. It might work on your machine and no one else's. And it might work sometimes and not the rest of the time. But can we solve that? This is a glue full screen scan line, right? It always works if you only care about the glue. But as I said, the shifter is involved as well. So this is a very unstable scan line. The reason we have a stabilizer is to clear the shifter and make it playable. So, can we do a stabilizer on this full screen scan line? Sure, we can add a regular stabilizer. But I don't like that. It's visible, it cuts off graphics at the far right. It also needs 2 instructions and nothing between, and well, that just screws up my code. So let's do the stabilizer someplace else. The only reason it's at the far right is that you don't want to disturb the screen. The only thing you want is to clear the line before the next line. So let's try making a stabilizer at the beginning of the next line. And the one I have, which is used in closure since demo that you saw yesterday, looks like this. I've added 1 instruction. I go to medium resolution at cycle 8, and then I expect the other ones. This is, of course, 16 cycles less used for moves than a regular full screen scanner. So I have more free time. I also only need to do stuff at 2 points. 1 big block for instructions in the beginning of the line, and 1 single move 8 cycles at the right corner. That means I can do movements more efficiently, since I don't need to break them up for the stabilizer. Does this work all the time and on all machines? It works really well on SD in wake state 1, wake state 3, and wake state 4. It works on wake state 2, but I have to have 2 versions, depending on whether the shifter is currently happy or unhappy. There are no better discussions. The shifter can be either or. It might be possible to detect which code should be used when, and so we would have solved the SD smart cycle. SDE, I consider to have been solved when I got here yesterday. I then tried closure on the combo machine. I fixed one of the problems that I could see, but the other one I would maximum resolution full screen on the Atari ST. It's weight state dependent. 415 pixels horizontal is what I get in weight state 2. 413, 412, 410 in the other weight states. 413, I think, on STE. 276 scan lines high. That is, of course, using the trick that has been documented several times, that you can indeed open 2 more lines at the very bottom by a lower order switch. You actually get a few pixels, about 18, on line number 277 as well, if you want to really break the record. No one has done full screen history before.
I did, but you didn't publish.
You didn't publish. Oh, well, the things that we've done. So that's something to strive for, and especially emulator writers are nowhere near this. So emulator writers need to be updated. That was all about understanding. Now I want to talk about SyncLock a bit. SyncLock was, when I started writing demos, one of the magic things. I did not figure that out by myself. I was in a demo crew that joined another demo crew, and after a while we became members of Sync, but before that, we got the secret to SyncLock from Redhead, who sits up here in Sync, and we were extremely happy looking at that really very, very stable raster in a border. I thought, wow, now we can do it all. A regular SyncLock is of course quite easy, and I should have been able to figure that one out. You read the video map and see how far have I gotten to the video map. You negate it, then you wait for an inverted amount of time, and you're locked. Alright, that's nice. That's basically what everyone does. You can either use the jump table, that was the first method used, or you can use the shift to do the wait. You need to use an image line to sync this way. You need to start the screen, get image data, and then sync it. So that's what everyone is doing. Unless you sync to HBL. That's interesting. HBL is the crappiest interrupt of them all in the ST. Once you see it, you go, oh wow, I'll use different rasters. And you realize that they start in, a few pixels in the left order, and they're completely unstable. They just jump back and forth. Crap, never use HBL again. Use Firebee. I love HBL. It was discovered by Igor that the instability of the HBL is the same for all the multi-vector interrupts, and is caused by the difference between the E-clock, 1 megahertz, of the 68,000 divided down. And it's predictable. So this whole instability can be compensated for. You can detect the pattern of the instability and then do an anti-pattern. So you can check how unstable is it, when does it repeat, and I wait the inverted amount of time, and I'm locked to the HBL. This pattern is actually exactly the same on all machines, ST and STE, but it's actually somewhat easier to write a code that dynamically detects it and compensates than detecting where you're on the pattern. This gives us an extra full screen scanner. You can sync lock to HBL at line 33, and you're locked and done when you need to open the left border, so you can use all scan lines for your full screen. Or, as we will get to, if you want to do sync scrolling, you can use additional scan line. And of course, closure is sync locked to HBL. I detect the pattern right off of the boot sector as well, and then the demo code actually runs this anti-pattern every BBL throughout the whole demo and stays in sync with the HBL. Sync scrolling.
This eClock collection has been done from the author of Spectrum 512 years and years ago. You had a mouse moving on the full color spectrum picture, and he needs to read the keyboard fascia, which also is affected by the eClock, and he corrected it in Spectrum 512. And that is the first place I know the eClock is corrected.
So I don't know if you ever heard, so I will repeat it. In Spectrum 512, to get data to read the mouse pointer, the author needed to correct for the E clock, which is the same instability for the offset between the CPU and the HGA chips. But I actually don't know how we compensated for it.
Just the software, he knows the pattern and he uses different routines to read the mouse pointer for different states of the E-clock.
Alright, so he knows about the pattern and he uses different routines to read from the HGA chips to compensate for it. I think that's amazing. Spectrum 512 was somewhat before its time. Pretty impressive. Alright, let's talk synchro. The name kind of implies it was invented by Sync, but it wasn't.
That's a bit.
In Sweden, we call it hardware scrolling, or hard scrolling. And as far as I understood, it was invented by Omega and TCB without knowing about it, both of them. I think I've seen the story. The flying egg calls up Ankle talking about who would have secret stuff. And Ankle talks about the secret stuff. And then flying egg mentions, well, we can scroll the whole line, the whole screen in 13 lines or so. Ankle replies, we need 15. Alright, so first released by TCP in the Kali demos. The same routines used in somewhat main menu and enchanted lands. They actually never changed the routine, as far as I know. They only used the left and right borders. Oh, I assume everyone knows how sync scrolling is done. If you make scan lines of different lengths, you will read different amounts of memory before the rest of the screen is shown. So by combining the different scan line lengths, you can offset the screen with how many bytes you want to have been read before it shows them. And the screen scrolls. Alright. Before we knew about wake states, we thought that it was pretty unstable to open scan lines. Left and right, tested through time. We kind of believe that those worked on all machines. So TCP used only those. That's why their demos has a color change background in the performer, and then the screen starts quite low down. Sync in switching year demo 8990 used a sync scroll routine which would need a 9 lines, using more combinations, line length combinations. Griffith in Circle made one that I think was used for many years, which used 7 seconds. And we're further today. So thanks to the research by Paulus Moos in 2012, we now have 12 line length combos. And these are all diffused. You can actually go and read the sync machine and just figure out if I do this and that, if I do this and that, if I do this and that, the line length will be this many cycles, which is of course this many bytes. And you get 12 combos to all the 128 offsets you need. And those are 4 lines. So a modern sync scroll needs 4 lines, and you sync scroll to the HBL, which people didn't used to do. So compared to older demos, you only need visible 3 lines to do your sync scroll, and you get graphics almost to the very top. That was all about the loop. Everything I've said so far, besides stabilization, has been about the loop. All the sync scroll has been about the loop chip. The cooler sync scrolls are using the shift loop. So separate chip, separate design, separate piece of code. And the very first example of this that was released is the 4-pixel full screen sync scroll by AM. And I will get back to how that is done. There is a 4-pixel non-full screen sync scroll that was done by LGBK, Paulus Moos. And that's amazing, both that it was done and that it hadn't been done before. And I'll get back to you on why. So, how does Aliens sync scroll work in the Punisher machine demo? This is a simplified shifter schematic, again by Alien. The important part here is that the shifter has 2 sets of registers. One set calls IR, and those are registers that when the enemy says, I've got video memory data for you, I've latched the address, read, the shifter reads 4 words in low resolution into those registers. Once it has read those 4 words, shifted out one bit at a time with a palette lookup onto the RGB data. Now this of course means that if you can put something in these IR registers so that the shifter actually starts outputting data after it having read 3 words, it will do so 4 cycles earlier than it would have if it had to read 4 words. And that's the concept of the 4 pixel sync scroll by Alien. Open the left border, go to medium resolution, and wait. Different amount of times depending on how much you want to scroll, and then go back to low resolution. And you do that every scanner. I had a discussion here during this weekend when people ask, why? What do you gain from doing this compared to a regular sync scroll? You can just pre-shift your graphics 4 times and you get a 4 pixel sync scroll. Well, you actually get to 16-bit boundaries, so you can do move instructions and pinpoint the move instructions on 4 pixel boundaries, where if you didn't do this, you would need to add more your content. So it's a lot more effective for those use cases. Has anyone here done full screen, exited your full screen back into your developer environment, and the bit planes have been screwed up? Everyone have done that. Now why did you not invent the 4 pixel non-full screen sync scroll? Because that's what it is. How to realize that that's stable. The bit planes are screwed up, and it's stable. Game is running. Interesting. Can we enforce that? Can we cause it to happen predictably? And that is what we invented in 2012. And there's a concept demo of a bee scrolling 1 pixel at a time, working on a 512K memory, which would be impossible otherwise due to how the amount of memory you need to appreciate. You start off at the top of the screen by unstabilizing the shifter. You go to high or medium resolution for a small time, then you go back and the shifter says, oh crap, I've got leftover words in my registers. And it keeps doing that. So it has 1 word at the end of the line. When the next line starts, it reads 3 words. Start the screen, that is 4 pixels earlier. Get to the end of the line, there's a 1 word left, and it's going to start the next line. After 3 words have been read, that's 4 pixels earlier, and you have a 4 pixel sync scroll. Now, I told you that the glue state machine is really stable. The shifter is not. I told you that the glue state machine is offset from the CPU, and we can prompt it. If I do this and that, it can detect which wait state that I'm in, and I know that then I should do these instructions at a certain point in time due to the wait state, and everything will be stable and nice. The shifter is not nice. This code currently works, and the trash report has been a slide. Let's go from memory. This code currently works in wait state 2, wait state 4, wait state 3 sometimes, or quite often actually, for all the 4 different positions. 0, of course, -4, -8, -12. Those are 1, 2, 3 words left in the shifter at the end of the line. In wait state 1, one of the positions, -12, doesn't work at all, which is the same for sometimes in wait state 3. So you will get 3 of the 4 needed positions to get to 4 pixels. However, 8 pixels always works. So that's nice. It's current research. I'm not going to tell you that it's impossible to fix. It doesn't seem likely. The reason for that is that the amount of time the shifter is idling at the end of the line is different between the different wait states. And it seems in wait state 1, which is the wait state I believe Atari wanted the whole shift to be in, maybe they thought the glue and CPU were synchronized, and is the wait state the SDE is in. It doesn't have wait state, but it acts like the wait state 1. The shifter actually clears the words at the end of the line, so you can't get this unstable condition. We have the banded screens, every other 16 pixels now. We have what's called Spectrum 512 pixels. You might remember that. So in Spectrum 512, sometimes you got a black dot and only power off your face. There's actually another condition which is pretty much caused by the same thing but different, where the color of the pixel that's displayed will be due to bus congestion, but two chips trying to access the bus at the same time. And so you get a value that is not in the play registers, is depending on which block has been traveling on the bus. We've talked about the glue and the shifter, but MMU at 16 megahertz can likely be offset from the glue and CPU as well, and maybe from both of them, and that's problematic. And some of these states are migratory. They shift when the machine is already up and running. So I'm going to show a brief video, and you might see some small 16 pixel, oh yeah you can, problems. And this is happening live. That screen was working, I left the machine on, and this started appearing. And it will continue to appear more and more. After a while, it might look like this. And that's not funny. I caused that to happen. It actually will not, should not happen. Maybe it will. So what do we know about the every 16 pixels? What causes? I mean, that's pretty interesting. How come every 16 pixels become black? It's only true for low resolution, by the way. In mono resolution, it's every fifth word, which gives some insight into what it is that's happening. So, I have some theories about it, which is quite tentative, sort of based on the fact that this is what it looks like in mono. This is, by the way, a right border removal in mono. As I said, this was not the final presentation due to the crash. And I have to do the rest from memory. It's likely that the shifter fails to read the data it needs into its IR registers. So it has no data, and the internal registers are thus flat. There has been, or border color, there has been no copy from the IR registers to the internal registers. This is my active area research right now. This is fun too. So how can we detect from software? That's the only thing that's interesting. How can we detect from software that the shifter has not been able to read from the address that MMU has matched? If you go to the source code of emulators, you will see comments that says, reading from these memory range of these registers will return random data. How do you get random data? That's difficult. Where do you find random data in Atari? I don't know. That's one place to look, because most often you will get the last data that has been
talk about two different STs for opening the upper border.
Yeah, I have one.
Is it true? Is it false? What's the problem?
Right, the question is, in the beginning there was talk about there being two different versions of the SD that had different open border heights. So I'll get back to a slide. And it will take a while. Yes, it's true. When Atari first made the SD, Atari is an American company, even though they never sold any computers in the US. And they thought, we're going to start the screen at NTSC at this position, and in PAL, more lines were started a bit fell down, and they released machines, and it was basically on some TV sets you could not see the top of the screen. So Atari had to make a new edition of the glue, which decides this, and insert that into machines. So really early SDs actually have a shorter top border. The glue takes the decision to start the screen earlier. But if you use the type of full screen scanline that I propose, you do not care about that. I am at 60 Hertz at the end of all scanlines.
Yeah, really.
Opening all
So the only thing I need to do is to avoid stopping the screen at the NTSC screen stop position and NTSC blank position, which are at lines 200 and 224. And 270, okay, 270. Thanks. If you don't want the extra two scanlines. So it is an issue, and you need to handle it if you want your code to work on all machines. Those will be short top order if you do the regular switching at the end of scanlines. But kind of the point of this presentation, don't do that. It wastes cycles and you don't need to. Any other questions?
Yes, the 508 cycle scan line for correcting the E-clock. How do you think about that?
Alright, so there's another way of synchronizing your code to the E-clock and get stable HDL, etc. And that is by realizing that if the VBL had been a tiny bit shorter, 16 cycles shorter, they would be missing. And how do you make your VBL 16 cycles shorter? Well, you use 4 scan lines of 60 Hertz. That works. But it's outside the step.
yes.
There are lots of cool sync tricks that have been made in demos over the years that do not actually follow the rules of the state machine. You can do a 0-byte scan line by cancelling H-sync for the next line. If you're lucky, your monitor and TV will handle it. If you're not, it will look weird. And there are many demos released with such strange effects because it worked on the computer and the TV set of the one who made it. I expect there are monitors and TVs that will not like being in 60 Hz for 4 scan lines during a VBL and the rest of 512.
Well, exists an international demo. It's like for 30 lines in 60 Hz. So who cares for 4 lines?
So it works. XXX International did it for the whole top border. I agree. On my TV, it was almost half the screen in the top border was outside the
But
border.
if you do the lines at the end of the PBL, it doesn't matter anymore because after the PBL sync, everything will be alright.
Sure. That's absolutely one way to do it.
And then your reading of the keyboard Asia will be stable too everywhere.
Yeah.
That's a big advantage.
Yeah.
Especially if you want to use the mouse.
I don't want to use the mouse. Have you used my Atari mouse? It's horrible.
But
it's lovely.
Other questions?
Yeah, that sounds good.
Yeah.
Any emulator developments? I mean, is this sort of going into there and if people are finding emulators?
Steam Stephen Siegel edition patched the emulator for the 508 cycle scan lines as soon as I released it.
So, since I analyzed the state machine and realized that emulators need to be 2 cycle exact to actually work in all different wake states, and you should have a simulator, I have been talking to the It's on the to-do. I briefly tried it. You could get a 14 byte long scanline by not getting to low resolution at 30 cycles, and it will, the computer will start a new H-sync and it will screw up the scanline badly. I thought that if I went to external sync, maybe it didn't throw a new H-sync, but it did not get that to work. So try it briefly.
I don't have any question because I'm a graphic artist and this goes way over my head. But I want to thank you for that extremely structured and analytical presentation. And it made me smile because it was. I think you remember the night when 67819 from Tech moved the right order. It was literally after half bottle of Gardens. And we were like falling asleep the next day. We woke up in the right order. The garden was sort of wondering how we did that. So I feel like having been in a presentation of the chemical and physical processes of rapid oxidization that happens when you burn stuff. And we were just rubbing sticks together back then. And look at what happens when you rub these sticks together real fast. So I'm very impressed. Thank you.
Well, thank you. I'm somewhat active in the retro scene. I get invited to interviews in magazines and shows on talking about retro computing. And when it comes to the Atari ST, I usually start off by saying that we didn't have training wheels on the bike like the Amiga had. We had to do everything ourselves. And then I bring up overscan and sync scrolling as the key developments on the Atari ST that made them a total difference. And we all know who started it all. So, thank you, exceptions. All right. No more questions? You can find. Sorry.
One more question about the black pixels. You said in low res it could be 16 pixels and in high res 5 pixels.
Every fifth.
Every fifth. And
Word.
you made something in low res. Because there I have never seen black pixels.
I have not caused it to happen in this. So the band screen, the around 16 pixels black, which is kind of maybe on copying of words, but the higher resolution is the fifth. I've been playing around very seldomly in medium resolution, so I haven't had it happen. It might not be that it can happen, I just haven't seen it.
You say it's stable in low res. What happens when you switch medium res then?
Sorry.
You say it's stable in low res, the shifter state.
Yes.
What happens when you shift into medium res?
Alright, so if I get a bad screen, this is by the way why my full screen scanline isn't these four instructions, but I go to this. So one way of solving a bad screen, if you get one, is to go briefly to medium resolution. One way to cause a bad screen, if you want to snoop the bus and see if you can detect it, is also to go to medium res and then exit to medium scanline and see if the line is bending. So obviously we are kind of forcing the shifter to get out of sync with something, which is pretty amazing in itself, that we can, in software, force it to hardware-wise get out of sync.
Yeah, I'm just curious because that's kind of crazy that you found the state machine for the blue. So that's not documented anywhere as a thing. So how did you reverse it to get to the very precise state machine?
So in a thread in Atari forum in 2012, Paulus Moos at UJK suddenly posted an Excel sheet where he documents for all the different wave states exactly what effects he sees doing switches at different cycles. I read that absolutely too much. We all have jobs and kids, and I don't know how I did it. And after a while I realized, come on, no one actually writes if then else in a chip in 1985. It doesn't happen. So it must be something else. Now the thing that you can do is a simple state machine. then did new stuff that hadn't been done before, and there's the new ones. Just by my state machine tells me this should work. I test it and it works.
So you need to test on a lot of different machines since you have the knowledge for all the machines. So do you have all the machines yourself? Where did you test all the different machines?
So how many machines have I tested on, since obviously my demo didn't work on the combo machine yesterday? I find Atari STs, and a few years ago I had none. So I have two STs, two STFM, and one Mega ST with a slow CPU clock of 8 megahertz. And I've additionally tested on other machines in sync members. So I did think it would be fully functional in all the machines. And this is why the original full-screen standline by Ilna in level 16 is so amazing. I don't know how many machines that one was tested on, but it still works today. It has worked since it was made, which is pretty amazing.
So how about Mega ST, Falcon, TT?
I briefly owned the Falcon, and then I saw Doom. And the email wasn't around to give us Doom quite with Falcon now. So I not played around on the Falcon at all. I also am a member of Sync, and the SDE is too useful for us.
It is. Yeah.
That was hard enough. So sorry, I haven't analyzed those machines at all. I might get a
Yeah.
If I remember correctly, Iger on Atari Forum just threw a bomb in and said, okay, I decapped the shifter, I have everything the shifter does. Has anyone contacted Iger, has bugged in about those plans or whatever? I mean,
So-
it could be essential to see what's going on there for you.
So Iger indeed has said that he has kept a lot of chips and analyzed it, and that's it. He doesn't need to release any information himself, and he feels it's complete. I don't know. And with the people who are doing this kind of research, and it goes for Paul as well, so surely me, I need to get back to my family. And all of a sudden we do the research in a few months, and then we wait a few years, and then we continue. So who knows, for the next ST week, maybe we'll have some new developments.
Did anyone try to get hold of the breadboard? Because it is known where they are. I think even the number where in the museum they are stored should be known. And there could be some information in it too, because it's essentially the wiring the shifter is made of.
So do we have access to the breadboards? I do not know if the breadboards are still there. Or
They are.
if they are, yes, I did. I think someone should actually try to get access to it. When I ask for access, people who do these spreadsheet things, even if they have these sort of museums, often like new developments and new insights that people care.
But it's in EUS, so it's protected by DMCA.
Probably.
Alright.
Do anybody does like full frame synchronization? You know, level 16, full screen doesn't have any frame synchronization. It's like fully, it fills the entire frame, and then they don't synchronize at all every frame. Like anybody else does that?
Yes, me. Lots of it.
Yes, you and myself have done that, running the whole stream without the synchronization.
I even did it in BASIC.
In basic. Oh, yeah, basic, yeah. Should be possible.
Don't mention this.
Yes, I have.
As far as I understand, this presentation is available.
A presentation is recorded, so it will be available via YouTube. We'll post
Tomorrow
it.
on YouTube.
Yeah.
Yeah, tomorrow. I have one question that is about out of scope, but maybe anyone knows why Atari choose the bitplane pixels for ST? Because from the coder's point of view, it's the most crappy way to organize screen.
I know the answer to that.
Is this chip?
No, it's because they wanted to do text scrolling fast, and text scrolling is faster with bit planes. It's not good for games, but it's good for text scrolling.
Why did Atari do replays? They foresaw the invention of chunky pixel with the movie Beans version, of course. Where now Atari is defeats the Amiga in doing 7 FPS demo effects.
Probably hardware designers are not coders and they just don't give a single about it.
Could be, could be.
Hey, here's your hardware and now it's your worry.
Alright, no more questions?